This circuit, blinking an LED from a 1.5 volt battery, is very popular on YouTube. It looks simple, but there's something special about it. How can a 1.5 volt battery power a 2.5 volt LED? Well, it's a combination of two very clever circuits. A relaxation oscillator and a charge pump. Let me start to explain the oscillator. We ignore C2, R3 and the LED for a moment. At the start, Q1 is off, C1 is not charged, and R2 is very small compared to R1. VBE will be much less than 0.6 volts and will not turn on Q1. Now C1 is slowly charged via R1 and R2. At some point, C1 will be charged close to 0.6 volt, so Q1 will turn on. When Q1 turns on, it will pull the base of PNP Q2, so Q2 will also turn on. Now something interesting happens. C1 is already charged enough to turn on Q1 a little already, but Q2 will pull on R2, lifting up C1 from this point. This means that the base of Q1 will be even more positive, so Q1 will pull even harder on the base of Q2 and C1 is pulled up even more. This loop will cause C1 to dump all its charge into the base of Q1 until it is empty, and then the cycle starts all over again. The oscillator speed depends on the time it takes for C1 to be charged via R1 and R2. To get a very rough feeling, we can multiply 1 megaohm with 1 microfarad, so one cycle will take about 1 second. To make sure that this circuit oscillates, R1 must be much bigger than R2. Otherwise, it may get stuck in a stable state. Now let's have a look at the charge pump at the right side of the schematic. The oscillator will periodically switch Q2 in pulses. So what will happen? C2 will charge via R3 and R2. At 100 microfarad and 1K, this will take roughly 1/10 of a second, much faster than C1 was charged. The LED will get 1.5 volt from the battery, so not enough to light up the LED, which needs 2.5 volts. Now when Q2 is switched on, something cool happens. R2 at the negative side of C2 is lifted to 1.5 volt very quickly. Now with C2 already being charged to 1.5 volt, this 1.5 volt is put on top of the battery of 1.5 volt. So now we have 3 volts over the LED, which is enough to light it up. The current will flow from the battery via Q2 and C2 into the LED. So there's no additional series resistance, so the charge of C2 will be dumped into the LED quickly and you get a bright flash. So this circuit is very clever and it needs to be tuned correctly. To oscillate, R1 must be much bigger than R2 and C2 must charge much quicker than C1. Now before we build and test the circuit, let me show the simulation in LTSpice. Here you see the schematic in LTSpice. You can download the simulation file on my GitHub page. Link is in the description. For the LED, I created a simplified LED model which matches the 2.6 volt 3 mm white LED I used. For the simulation, I set the stop time at 5 seconds. Let's run the simulation. Now let's have a look at the current through the LED D1. There are short current peaks of about 40 milliamps. Let's add two cursors. So the blink frequency is about 1.2 Hz. Now let's zoom in a bit and add another two cursors. You see the pulse is very short, about 7.5 milliseconds. So it's really a very short flash. Let's remove this trace and let's check the voltage on the LED. This is the battery voltage. And here Q2 is switched on, so the voltage goes up to almost 3 volts. And C2 is discharged into the LED. That is the effect of the charge pump. Here at the side, I have another LED of the same type with a current source. And you can check the forward voltage is 2.6 volt at 20 milliamps. So this is the peak at 40 milliamps, then the voltage goes down, and at about 2.2 volts, the LED stops conducting. Finally, let's quickly compare the charging of C1 and C2. Let's first close this one. Now you can use math and stuff, but it's much easier to move Mother Earth from here to the midpoint of the capacitors. Now let's simulate again. You see C1 is charging up to almost 500 millivolts before Q1 switches on. Then let's have a look at C2. C2 is charging and is fully charged when C1 triggers Q1. Then C2 discharges, but not completely. And this is because the LED needs at least 2.2 volts to conduct, so the capacitor cannot fully discharge. As mentioned, you can download the simulation file on my GitHub page. I really recommend you to have a look at LTSpice. Good. That was enough theory. Let's build this circuit and power it up. Here you see the circuit running and the signals on the two capacitors on my Handtech oscilloscope. I connected the ground between the two capacitors. The green trace is the voltage on C1, channel 2. The yellow trace is the voltage on C2, channel 1. You see that the voltage on C1 goes negative. That makes sense because C1 is charged to 0.5 volt. But when Q2 switches on, this point is lifted up to 1.5 volts, much higher than this point, so it is quickly discharged to a negative voltage. Now let's put this in normal mode and have a look at the frequency. 1.3 Hz, so that's pretty close to the simulation. The flash of the LED is actually too short for the camera to capture it. I hope you liked the video. If it was useful for you, please like and subscribe, and leave your experiences in the comments.